Hello everyone, so today we've got a Calc 2 problem involving work. Work problems are one of the applications you typically do in a Calculus 2 or 1 class. Now, what we have here is the following. Find the work required to pump out the water from a trough, shown below, for which is filled with water to a height of 4 meters. So we have this trough here, which looks like this rectangular prism, and it's got a length of 5 meters, a width of 3, and a height of 7, and the water is filled all the way up to 4 meters from the bottom. All right, now the main equation here that we're going to be working with is work equals force times distance. And we're going to break that down a little further here because of the fact that this is an equation involving, a problem involving water or any liquid really, and finding the work done. And the setup will be very similar to any scenario that you have. Force equals mass times acceleration. And we have acceleration, actually, that's a constant, that's 9.81 per meters per second squared. Let's keep that in mind that there are constants that you have for acceleration, and it all depends what units you're using. So here we're using meters, so that's why I said 9.81 meters per second squared. So force equals mass times acceleration. So we have acceleration, but what about mass? We don't have like a mass of anything given here. However, here's how we're going to do this. We know that mass over volume is equal to density, and mass equals density times volume. You just multiply both sides by that equation up here by volume, and that cancels that. And we actually have the density of water. That's 1,000 kilograms per meter cube. And that equation that I have, like F equals ma, becomes density times volume times acceleration. And yeah, I can work with volume here, as I said. Now, how is that? So if you were asked to find the work required to pump the water out of the trough, the idea would work as follows. I cut out a little representation of a piece of basically, just the amount of water that I would need to move up to the top. That's the picture you see here with the piece that looks like it's like a piece of lumber here, okay? And the idea is you can take the water, all that water that's raised up to 4 meters, and you can basically cut that into smaller pieces, as I am doing there. And what I want to do is I want to get a general equation for finding the work required to move a piece up to the top, and that applies to every one of these pieces. And if you add up all the work for all these pieces, that gives you an approximation to the work required to take all the water up to the top of the trough, okay? What you need to do, though, with all these problems is you need to set up a system here to a scale, basically, or a coordinate system. And I have 0 down on the bottom, and then I have these values x sub I and xi sub plus 1. So x sub I just stands for some distance away from the bottom. Xi plus 1 is just some other distance from the bottom. And yes, we need that because what we're going to see in a minute is that there are some values that are changing here. And also, you just think about it this way, like a piece of water that you need to move to the top, it's a different distance because it all depends on where you're at with respect to the trough. So if I took a little chunk of water, another piece of lumber, and then it was closer to the bottom, I'm going to move that piece more than I would one that's closer to the surface of the water. So that's why we're going to involve a variable, first of all. Now, the volume of that piece of wood drawn over here. I know it doesn't look like it, but again, that's sorry, that's the closest I can do in terms of my art here. That piece is 5 meters long. It's got a height of change of x. Change of x just stands for the difference between the two x values, and it's a width. That width is changing each time here, okay? The width of the piece right here would be different from the width of the piece, like if I had it up here. So I need an equation, or I really want to get an equation in terms of, let's say, x here, So I can work with this in terms of calculus and whatnot. So how do I do that? Well, what you want to use is things that you have at your disposal. And one thing you have is similar triangles. If you took the triangle that makes the face of this trough, this is 3 meters and this is 7 for height. If you took that piece that I'm like focusing on, that piece of lumber, this piece would have some width W and some height X from the bottom, or X sub I here. Okay? These triangles are similar, and you would have that 3:7 as W is to X sub I, or 3/7 X sub I equals W. Yes, so similar triangles have this property that if you take the length of one side to another, you would have that same ratio on the other triangle, corresponding ratio, okay? And yeah, these triangles are similar because all the angles are pretty much the same, okay? So just think about that for a second. And yeah, often you will use geometry to set this up. So my volume equation for that piece would equal 5 times 3/7 xi times change of x. All of that would equal my volume, okay? Simplifying that, that becomes 15/7 x of I change of x. And then you would have rho times volume, density times volume times acceleration. So I put all that together, and that is what you see here. So F sub I just represents the force of a piece of the water here, okay, that piece of lumber, as you can say. Okay, now we also had the distance here. And the idea with the distance, and this is the actual answer, but let's see how we get the answer. Let's go back to the picture here. The idea is the following. If you took this piece and I asked you, how much do you need to move that piece up to the top? Because that's, yeah, eventually if you want to pump that water out, you have to take the piece up to the top. Well, it would be whatever distance you have here, x. You have to consider how much distance this piece is from the bottom, and then it'd be 7 minus that, so 7 minus xi. So another way to think about it, just for a second, if I'm just making this up, if this was 2 meters, then how much would I need to move the piece all the way to the top? Well, it's 5, because you still have 5 meters to go because you have a height of 7. So it's 7 minus the distance from the bottom, so 7 minus xi, so that's why you see that. So total for the work for that piece, it would be F of I times D sub I, and work itself would be equal to a sum of all those pieces, which represents this. However, that's an approximation. It's not really the whole thing, okay? It could be a very good approximation if you have an infinite number of pieces, and when you have an infinite number of pieces, you get an integral here, okay? So essentially, what you'd have here is an integral that goes from, and my apologies, I forgot over here to simplify this over here. But anyways, this comes out to be the 9810 15/7 x times x of I, 7 minus xi times the change of x here, okay? Anyways, all of that turns into what you see here. You can think of the change of x turning into the dx, the 7 minus xi is 7 minus x, 15/7 xi, 15/7x, and then 9810 here. Sorry, I had the unsimplified form there, 9810. And there you go. You would just go ahead and integrate that. Usually the integration is actually the easiest part of all these. It's the setup, okay? So if I were just to go over this real quick, just the major steps here. We're using the fact that work equals force times distance, force equals mass times acceleration. Force in this case is going to equal density times volume times acceleration. And yeah, you're getting a volume of a part of a piece that you're going to be moving up, okay? And the hardest part usually is setting up something that varies, if anything, like some kind of a dimension here. In this case, it was the width of the of each of those rectangular pieces, like those lumber pieces. Anyways, you set these up and you get your integral, and yeah, the integral is usually okay. And yeah, and the units here are in joules. Okay. All right. Well, I hope this helps. Thank you for your time.